Picture the darkness between stars. Not the familiar darkness of Earth's night sky, painted with the warm glow of distant suns, but true darkness. The kind that exists in the vast emptiness where light itself becomes a stranger, traveling for years just to whisper from one point of existence to another. In this profound silence, something moves. It drifts through the cosmic void with the patience of geological time, carrying within its frozen heart the memory of another sun. A sun that may have died before our own Earth learned to breathe. This wanderer has no name in its native tongue, no story written in the language of its birth world. To us it is simply 3i Atlas, the third interstellar messenger to cross the boundaries of our solar neighborhood. Only 3 times in recorded human history have we witnessed such visitors. 3 times, objects forged in the gravitational embrace of alien stars have wandered into our cosmic backyard, each one rewriting what we thought we knew about the universe beyond our borders. The first was Oumuamua, the scout from afar, a needle of rock and metal that tumbled through our system in 2017, spinning end over end like a cosmic cigarette, defying explanation with its strange acceleration and mysterious composition. It came and went before we could truly understand what we were seeing. The second was Borisov, the wandering snowball, a more familiar sight in 2019, dragging behind it a tale of gas and dust that spoke of distant icy worlds and the chemistry of alien star formation. It behaved more like the comets we know, yet carried within its frozen nucleus the isotopic fingerprints of another stellar system entirely. And now comes Atlas. As it drifts through the outer reaches of our solar system, something extraordinary is happening. Something that challenges every assumption we've made about these interstellar wanderers. Atlas is not simply passing through our neighborhood like a cosmic tourist. It is performing an act that seems almost biological. It is leaking, not the gentle sublimation of ice we expect from a comet warming in our sun's distant embrace. No, Atlas is hemorrhaging water into the void, vast quantities of it, as if somewhere in its crystalline core, a faucet has been turned on that cannot be shut off. The escaping vapor streams behind it like the exhaust of some impossible engine, writing chemical equations across the darkness in letters made of hydrogen and oxygen. But here is what keeps astronomers awake at night, staring at their data with a mixture of wonder and unease. The water itself is not the mystery. Water is common in the universe. What haunts them is what this water represents. When we detect H2O escaping from an object born around another star, we are not simply observing chemistry. We are reading a message, a note written in the universal language of molecular bonds, sent across the galaxy from a world we will never see, carried by a messenger that has traveled for millions of years through the cosmic dark to reach us. What story does this water tell? What secrets does it carry about the planetary system that gave birth to this wanderer? And why, in the span of less than a decade, have 3 such objects found their way to our cosmic doorstep? The universe, it seems, is trying to tell us something. Each visitor arrives bearing gifts of knowledge wrapped in riddles of physics and chemistry that push the boundaries of our understanding. They come not as invaders or harbingers, but as teachers from classrooms we cannot imagine, carrying lessons written in the fundamental forces that govern all matter everywhere. As Atlas continues its lonely journey through our solar system, shedding pieces of itself with each passing day, we find ourselves confronted with a question that reaches to the very heart of our place in the cosmos. Are we witnessing random chance? The statistical inevitability of objects wandering between stars? Or is there something more purposeful at work here? Something that suggests the universe is far more connected, far more intentional than we ever dared to imagine? The answer lies waiting in the tail of vapor that streams behind this cosmic visitor, written in a language older than Earth itself. July 2025 arrived with the quiet intensity of summer heat building over the Arizona desert. At the Catalina Sky Survey, astronomers were engaged in their nightly ritual of scanning the darkness for the unexpected. Most discoveries in astronomy come slowly, revealing themselves over weeks or months of careful observation, like flowers blooming in extreme slow motion. But sometimes the universe delivers a surprise that changes everything in a single moment. The first indication that something unusual was happening came not from the visible light telescopes that had been tracking Atlas since its discovery, but from an entirely different part of the electromagnetic spectrum. NASA's Swift Observatory, originally designed to detect the violent gamma-ray bursts from dying stars, had turned its sensitive ultraviolet instruments toward the approaching comet as part of a routine observation campaign. What it found defied immediate explanation. The comet was glowing, not with the reflected sunlight that makes planets and asteroids visible in our night sky, but with its own ethereal luminescence. In the ultraviolet portion of the spectrum, invisible to human eyes but crystal clear to Swift's detectors, Atlas blazed with an intensity that spoke of chemical reactions occurring on a massive scale. Dr. Sarah Chen, the principal investigator on the Swift team, would later describe that moment of discovery with the careful language of a scientist trying to contain her astonishment. "When we first saw the UV signature," she said, "we thought there might be an error in our calibration. The signal was so strong, so consistent, that it seemed impossible for a comet at that distance from the sun. But the instruments were working perfectly. What they were detecting was the spectral fingerprint of hydroxyl radicals, O molecules, flooding space around the comet like an invisible cloud. These simple molecular fragments are the chemical children of water, born when H2O encounters the harsh ultraviolet radiation of our sun and breaks apart, releasing its components into the vacuum of space. The amount of water vapor required to produce such a signal was staggering. Initial calculations suggested that Atlas was ejecting water at a rate equivalent to filling an Olympic-sized swimming pool every few hours. For a comet still millions of miles from the sun, where the solar radiation should barely be strong enough to sublimate surface ice, this level of activity bordered on the impossible. "It was like watching a fire hose running in the dark," Chen would later write in her preliminary report. "Except the hose was connected to something we couldn't see, powered by an energy source we couldn't identify, spraying a substance that shouldn't have been flowing at all." The discovery sent ripples of excitement through the astronomical community. Here was an interstellar visitor behaving in ways that challenged fundamental assumptions about how comets work. Most comets remain dormant until they approach within a few astronomical units of the sun, where increasing solar radiation begins to heat their surfaces and drive off volatile materials. Atlas was demonstrating robust activity at distances where most comets would remain frozen solid, but the mystery deepened when additional observations revealed something even more puzzling. The water vapor wasn't being released uniformly from the comet's surface. Instead, it appeared to be jetting from specific locations, creating a complex pattern of emissions that varied with the object's rotation. Whatever was driving this outgassing, it wasn't simply solar heating acting on exposed ice. Ground-based observatories around the world began turning their instruments toward Atlas, each one adding new pieces to a puzzle that grew more complex with every observation. The Atacama Large Millimeter Array detected not just water vapor, but also traces of other molecules, carbon monoxide, methane, and exotic compounds that spoke of chemistry occurring under conditions unlike anything found in our own solar system. As the data accumulated, a picture began to emerge of an object unlike any comet in our experience. This was not simply a chunk of dirty ice wandering between stars. This was something far more sophisticated, far more active, carrying within its structure the chemical signature of processes that might have occurred around an alien sun billions of years ago. The implications were profound. If Atlas was indeed leaking water at such prodigious rates, it was essentially broadcasting its composition to anyone with the instruments to listen. And what it was saying challenged everything we thought we knew about the formation and evolution of planetary systems throughout the galaxy. Meanwhile, in laboratories around the world, scientists began the painstaking work of analyzing the spectral data, searching for clues about the comet's origin and the forces driving its unusual behavior. Each new measurement brought fresh surprises, fresh questions, and a growing sense that we were witnessing something unprecedented in the history of astronomical observation. To understand what Swift Observatory was seeing, imagine trying to read a letter written in invisible ink, revealed only under a very specific kind of light. The ultraviolet portion of the electromagnetic spectrum serves as that revealing light for the chemistry of space, making visible the molecular signatures that remain hidden to our eyes. When water molecules encounter the intense ultraviolet radiation streaming from our sun, they undergo a transformation as fundamental as ice melting into liquid. The energy breaks the molecular bonds that hold hydrogen and oxygen together, liberating individual atoms and creating hydroxyl radicals, those OH fragments that Swift was detecting in such abundance around Atlas. The process happens with the mathematical precision of a chemical equation written across the cosmos: H2O plus UV photon, OH plus H. Simple in its elegance, profound in its implications. What made the observations of Atlas so remarkable was not just the presence of these hydroxyl signatures, but their intensity and distribution. The comet was producing OH radicals at a rate that suggested an enormous parent population of water molecules. For every OH detected, dozens of water molecules had been sacrificed to create it. Dr. Dennis Bodowitz of Auburn University, one of the world's leading experts in cometary composition, described the phenomenon with characteristic scientific precision tinged with wonder. "When we observe these hydroxyl signatures," he explained, "we're essentially watching the dissociation of water in real time. We're seeing the molecular bonds that formed in an alien star system being broken by the light of our own sun." The spectroscopic analysis revealed layers of complexity that deepened the mystery. The OH radicals weren't distributed evenly around the comet, as would be expected from simple solar heating of surface ice. Instead, they formed distinct jets and streamers, suggesting that the water was emerging from specific locations on the nucleus, driven by forces operating beneath the surface. Even more intriguing were the subtle variations in the spectral signatures themselves. Different isotopic ratios of hydrogen and oxygen hinted at formation conditions unlike anything found in our own solar system. The deuterium to hydrogen ratio, in particular, spoke of water that had condensed from the primordial nebula surrounding a different star, under different conditions of temperature and pressure. This isotopic fingerprinting represents one of astronomy's most powerful tools for understanding the origin and evolution of matter in the universe. Just as forensic scientists can identify the geographic origin of a person from trace elements in their hair, astronomers can read the birth conditions of celestial objects in the isotopic ratios of their constituent atoms. The water streaming from Atlas carried isotopic signatures that told a story spanning millions of years and countless light years of space. It spoke of formation in the outer reaches of an alien star system, where temperatures were cold enough for water to condense directly from gas to solid, trapping within its crystalline structure the chemical memory of another world. But the most remarkable aspect of the discovery was the sheer scale of the water emission. Preliminary calculations suggested that Atlas was losing water at a rate of several tons per second, a hemorrhaging of H2O that would have stripped a typical Earth-sized reservoir dry within a matter of days. This raised profound questions about the comet's internal structure and composition. Where was all this water coming from? How could an object just a few kilometers across contain enough frozen water to sustain such prodigious emissions? And what energy source was driving the sublimation process at such enormous distances from the sun? The answer, researchers began to suspect, lay not in the familiar physics of solar heating, but in something far more exotic. Something happening deep within the comet's core, where pressures and temperatures might create conditions unlike anything found on the surface of a typical comet. As the hydroxyl signatures continued to stream across Swift's detectors, painting their invisible portraits of molecular destruction and renewal, astronomers found themselves confronted with a humbling realization. This visitor from another star was writing its autobiography in the universal language of chemistry, and we were only just beginning to learn how to read it. The fire hose from the stars was not simply spraying water into space. It was broadcasting a message, encoded in the fundamental bonds between atoms, about the conditions that exist in planetary systems throughout the galaxy. Every OH radical detected was a word in that message. Every spectral line was a sentence describing processes that occurred under alien suns we would never see. And the message was just beginning. In the gentle cadence of scientific discourse, Dr. Dennis Bodowitz offered an observation that would haunt the imagination of anyone who heard it. When we detect water vapor from an interstellar object like Atlas, we're not just observing chemistry. We're reading a note from another planetary system. The profundity of that statement settles slowly. like morning mist revealing a landscape previously hidden in darkness. This is not simply H2O sublimating from the surface of a wandering iceberg. This is water that condensed from the primordial clouds surrounding an alien star water that may have once existed as vapor in the atmosphere of worlds we cannot imagine. Water that carries within its molecular structure the chemical autobiography of a planetary system born light years from our own. Consider the journey this water has made. Billions of years ago, in the outer reaches of a star system whose name we will never know, temperatures dropped low enough for water vapor to crystallize directly from gas to solid. The process occurred grain by grain, molecule by molecule, in the shadow of giant planets that may have been even more magnificent than our own Jupiter and Saturn. Those ice grains, accumulated slowly over millions of years, pulled together by the gentle embrace of gravity into larger and larger aggregates. Eventually, they formed the nucleus of what would become Atlas, a time capsule of frozen chemistry carrying the isotopic fingerprints of its birth world, locked within crystalline matrices of incredible complexity. Then came the disruption. Perhaps a gravitational encounter with a massive planet ejected the proto-comet from its home system. Perhaps the death throes of its parent star blasted it into the interstellar void. Or perhaps some cosmic catastrophe, the collision of planetesimals, the passage of a rogue star, the complex gravitational dance of a multiple star system, sent it tumbling into the darkness between worlds. For eons beyond counting, Atlas wandered through the galactic night. It passed through regions where space itself was different, where cosmic rays from dying supernovas had different energies, where the interstellar medium carried the chemical exhaust of stellar populations, unlike our own, where temperatures approached absolute zero, and time itself seemed to slow to the rhythm of atomic decay. And now, after a journey that spanned geological ages and astronomical distances, this messenger from another world has arrived in our solar system, carrying its cargo of alien water toward an appointment with our sun. As solar radiation began to penetrate the comet's outer layers, the ancient ice started its slow transformation back to vapor. But this is not ordinary sublimation. This is the resurrection of water that died as vapor around another star and is being reborn as vapor around our own. The H2O molecules streaming away from Atlas are immigrants from a distant stellar system, temporary refugees from a world we will never visit. The emotional weight of this realization is almost overwhelming. Every water molecule detected by Swift Observatory represents a connection across space and time to processes that occurred in the primordial disk of another star. We are witnessing the slow dissolution of ice that formed under alien skies, watching as the chemical heritage of another world disperses into our own cosmic neighborhood. But the water carries more than just isotopic signatures and chemical memories. It carries information about the physical conditions that existed during its formation. The crystalline structure of ice varies depending on temperature and pressure, creating different forms with different properties. By analyzing the way Atlas is water sublimes, the temperatures at which it transitions from solid to gas, the rates at which different phases change state, scientists can reconstruct the environment in which this ice originally formed. The preliminary data suggests formation conditions subtly different from those found in our own outer solar system. Slightly different temperatures, different pressures, different abundances of trace elements that would have been incorporated into the growing ice matrix. These differences speak of a planetary system with its own unique architecture, its own pattern of giant planets and small bodies, its own history of formation and evolution. Perhaps most remarkably, the water from Atlas may once have been part of an ocean. Not an ocean on the comet itself, but an ocean that existed on some long-destroyed world in its birth system. Water cycles between different reservoirs in planetary systems. Oceans, atmospheres, polar ice caps, and the frozen bodies of the outer reaches. The H2O now streaming away from Atlas as vapor may have once fallen as rain on an alien world, may have filled seas under foreign constellations, may have been the medium in which entirely different forms of chemistry, perhaps even life, once flourished. This possibility transforms our perception of what we are witnessing. We are not simply observing the sublimation of interstellar ice. We are potentially watching the evaporation of alien oceans, the final dispersal of water that may once have reflected the light of stars we cannot name, in skies painted with auroras born from magnetic fields we cannot imagine. The note from another star that Dr. Bodowitz described is written in a language older than Earth itself. It speaks of processes that govern the formation and evolution of planetary systems throughout the galaxy. It tells us that the chemistry of life, at least the chemistry that makes life possible, is not unique to our corner of the universe. And as Atlas continues its journey through our solar system, shedding pieces of that distant world with each passing day, we find ourselves in the extraordinary position of reading a message that was written before our own world learned to dream. Beneath the elegant simplicity of water vapor streaming into space lies a hidden complexity that speaks to processes occurring deep within the heart of Atlas. The comet's behavior suggests internal chemistry far more sophisticated than the simple solar heating that drives most cometary activity. Traditional comets behave with predictable patterns. As they approach the sun, increasing solar radiation heats their surfaces, causing surface ice to sublimate directly from solid to gas. The process typically affects only the outermost layers, creating activity that correlates directly with distance from our star. Move closer, get warmer, sublimate more ice. The relationship follows well-understood physics with mathematical precision. Atlas defies this comfortable predictability. Detailed analysis of the water emission patterns reveals something extraordinary. The comet is displaying activity levels typical of objects much closer to the sun. At its current distance, conventional physics suggests it should be releasing perhaps 3 to 5% of its surface area to active sublimation. Instead, Atlas shows nearly 8% of its surface contributing to the massive water outflow. This seemingly small numerical difference represents a profound departure from expected behavior. It suggests that whatever is driving the comet's activity operates according to principles that extend beyond simple solar heating. Something else is at work here, something that transforms Atlas from a passive chunk of ice into an active, almost living system. The most intriguing possibility involves crystallization processes occurring deep within the comet's interior. When water ice forms rapidly under extremely cold conditions, it often assumes an amorphous structure, essentially frozen water in a glass-like state that lacks the organized crystal lattice of normal ice. This amorphous ice is metastable, meaning it exists in a state of suspended chemical tension, like a spring compressed and held in place by the extreme cold of interstellar space. As Atlas approaches our sun and begins to warm ever so slightly, that amorphous ice may be undergoing a phase transition, reorganizing itself into the more stable crystalline form. This crystallization process releases energy, heat generated not by external solar radiation, but by the internal rearrangement of molecular bonds that have been locked in tension for millions of years. The energy release from crystallization could explain Atlas's anomalous activity levels. The comet is not simply being heated from outside by our sun, it is being heated from within by the reorganization of its own internal structure. It is essentially digesting itself, converting stored chemical potential energy into the thermal energy that drives water sublimation. But crystallization may not be the only process at work. Spectroscopic analysis has detected trace amounts of carbon monoxide and other volatile compounds mixed with the water vapor. These molecules sublime at different temperatures and under different conditions than water ice, suggesting that Atlas's interior contains multiple reservoirs of frozen volatiles, each responding to warming in its own unique way. The distribution of these different compounds within the comet's structure could create a complex internal chemistry. As some volatiles sublimate and migrate through the porous interior, they could encounter other compounds, triggering chemical reactions that release additional energy. The comet could be sustaining a cascade of chemical processes, each one feeding energy into the next, creating an internal chemistry that operates like a slow-motion explosion occurring over months or years. Even more intriguing is the possibility that Atlas contains materials that don't exist naturally in our solar system. Different stellar environments produce different chemical elements in different abundances. An object formed around a metal-rich star, or in a system with unusual isotopic ratios, might contain compounds that behave in unexpected ways when exposed to the radiation environment of our own stellar neighborhood. These exotic materials could be driving chemical reactions that have never been observed in terrestrial laboratories or in comets native to our solar system. Atlas could be demonstrating chemistry that represents an entirely new category of processes driven by the unique conditions that existed in its birth environment and activated only now as it encounters the specific radiation and temperature regime of our own sun. The implications extend far beyond the behavior of a single comet. If interstellar objects can carry exotic chemistry between star systems, they represent vectors for the spread of chemical complexity throughout the galaxy. Each wandering comet becomes a seed carrying not just water and organic compounds, but entirely new forms of chemical reactivity that could influence the development of planetary systems they encounter. As Atlas continues to demonstrate its anomalous behavior, astronomers find themselves confronting the possibility that the universe is far more chemically diverse than previously imagined. The standardized models of planetary formation and cometary behavior, based on objects native to our own solar system, may represent only a small sample of the chemical possibilities that exist throughout the galaxy. The comet from another star is teaching us that chemistry itself may be more varied, more creative, more surprising than we ever dared to hope. And we are only beginning to decode the lessons written in its vapor trail. From the rust-colored surface of Mars, Atlas would have appeared as a ghostly apparition crossing the star-filled sky. The red planet, positioned at just the right angle and distance during the comet's passage through the inner solar system, became an inadvertent observatory, offering a unique perspective on this visitor from another star. NASA's Mars Reconnaissance Orbiter and the European Space Agency, Mars Express, found themselves in the extraordinary position of observing an interstellar comet from the vantage point of another world. Their instruments, designed to study the Martian atmosphere and surface, were redirected to capture images and spectra of Atlas as it swept through the inner solar system, with its magnificent tail streaming behind. The view from Mars revealed something that Earth-based observations had only hinted at. Atlas's tail stretched across an impossible distance, extending for millions of kilometers in a gossamer thread of water vapor and dust that caught and scattered sunlight in ethereal patterns. From Mars's perspective, the tail appeared to span several degrees of sky, longer than the apparent width of the full moon as seen from Earth. But the most remarkable revelation came when the Martian orbiters turned their ultraviolet spectrometers toward the comet. What they saw challenged every assumption about cometary tails and the behavior of water vapor in the vacuum of space. The tail was not uniform. Instead of the smooth, continuous structure expected from simple solar wind pressure acting on sublimated materials, Atlas displayed a complex, braided architecture. Multiple streamers twisted around each other in patterns that spoke of magnetic fields, plasma interactions, and chemical processes occurring on a scale that dwarfed anything seen in comets native to our solar system. More mysteriously, the tail showed distinct color variations when observed in different wavelengths of ultraviolet light. Some sections glowed with the characteristic signature of hydroxyl radicals, while others displayed the spectral fingerprints of excited water molecules, carbon monoxide, and compounds that defied immediate identification. It was as if the comet was painting a rainbow across space, each color representing a different chemical story. Dr. Maria Santos of the European Space Agency's Mars Express team described the observations with barely contained excitement. We were seeing chemical differentiation happening in real time. Different compounds were being released from different regions of the nucleus, creating distinct streams within the tail. It was like watching the comet sort its own chemistry as it traveled. The Martian perspective also revealed something that Earth-based observers had missed entirely. The tail was not simply being pushed away from the sun by solar wind pressure. Instead, it showed clear evidence of interaction with the interplanetary magnetic field, creating spiral structures and periodic brightening that suggested the comet's plasma environment was far more complex than anyone had anticipated. This complexity pointed to something profound about Atlas's internal composition. The different chemical streams in the tail implied that the comet's nucleus was not homogeneous, but rather consisted of distinct regions with different compositions, different volatilities, and different responses to solar heating. It was a differentiated object, much like a miniature planet with different chemical provinces locked within its frozen structure. The implications were staggering. Most comets are thought to be relatively primitive objects, frozen remnants of the early solar system that have remained largely unchanged since their formation. But Atlas appeared to be something more sophisticated, an object that had undergone chemical differentiation. perhaps through heating events in its original star system, or through processes that occurred during its long journey through interstellar space. Perhaps most remarkably, the Martian observations suggested that different parts of the tail were interacting with each other as they streamed away from the nucleus. Chemical reactions were occurring not just on the comet's surface, but throughout the extended coma and tail system. Atlas was not simply shedding materials into space. It was creating a mobile chemical laboratory that extended across millions of kilometers of interplanetary space. The view from Mars also provided crucial data about the temporal evolution of the comet's activity. By observing Atlas over several Martian days, the orbiting spacecraft were able to track changes in tail structure and composition that correlated with the comet's rotation period. Different phases of the nucleus were exposing different chemical reservoirs to solar heating, creating a complex temporal pattern of emissions that told the story of the object's internal architecture. As the observations accumulated, a picture emerged of an object unlike anything in our experience. This was not simply a dirty snowball wandering between stars. This was a chemically complex, internally differentiated world in miniature, carrying within its structure the geological and chemical history of an entire alien star system. From the perspective of Mars, that ancient world that once harbored flowing water and a thicker atmosphere, Atlas must have seemed like a messenger carrying news from a distant cousin, another planetary system where water and chemistry had once written their own stories across the surfaces of alien worlds. The red planet, locked in its current frozen state, bore witness to the slow dissolution of water that may have once flowed in liquid form around another star. In the grand theater of the solar system, Mars served as a silent observer, watching as chemistry from another world dispersed into the cosmic wind, carrying its secrets toward destinations unknown. And in that moment of observation, two worlds touched by water, one ancient and desiccated, the other a frozen messenger from the stars, shared a connection that spanned both space and time, united by the universal chemistry that makes worlds possible. In the growing catalog of interstellar visitors, a pattern emerges that speaks to something profound about the diversity of planetary systems throughout the galaxy. Each object that has crossed into our solar neighborhood has arrived carrying its own unique signature, its own chemical fingerprint that tells a different story about the conditions that exist around other stars. Oumuamua, the first confirmed interstellar visitor, presented astronomers with a puzzle wrapped in an enigma. Its elongated shape, roughly 10 times longer than it was wide, suggested formation processes unlike anything seen in our own solar system. It displayed no detectable water emissions, no cometary activity, yet accelerated away from the sun in a manner that implied some form of outgassing too subtle for our instruments to detect. The object's composition remained largely mysterious. It reflected sunlight in a pattern consistent with metal-rich rock, perhaps similar to the iron-nickel composition of some asteroids, but its trajectory and acceleration suggested it might contain frozen gases that sublimated without producing the characteristic coma and tail of a conventional comet. Oumuamua was dry, dark, and deeply enigmatic. 2 years later, 2I Borisov presented an entirely different character. This second interstellar visitor behaved much like the comets we know, developing a prominent coma and tail as it approached the sun. But spectroscopic analysis revealed that its chemical composition was dominated by carbon monoxide rather than water, a signature that spoke of formation in the extremely cold outer reaches of its birth system, where temperatures were low enough for carbon monoxide to condense into solid form. Borisov's carbon monoxide abundance was extraordinary by the standards of our solar system. Our native comets typically contain CO in much smaller proportions, mixed with water ice and other volatiles. But Borisov was essentially a giant dirty snowball of frozen carbon monoxide, suggesting formation conditions that were both colder and more carbon-rich than those that existed in the outer regions of our own primordial solar nebula. Now Atlas arrives with its own distinctive signature, massive water emissions that dwarf anything seen in the previous visitors. Where Oumuamua was dry and Borisov was rich in carbon monoxide, Atlas hemorrhages water vapor at rates that suggest a composition dominated by H2O ice. 3 visitors, 3 completely different chemical stories. This diversity is not random. It speaks to the wide range of conditions that exist in planetary systems throughout the galaxy. Each interstellar object serves as a chemical core sample from a different stellar environment, carrying within its composition the signature of the specific conditions that existed during its formation. The implications are profound for our understanding of planetary formation and evolution. If our own solar system is typical of the galaxy as a whole, we might expect interstellar visitors to show compositions similar to our own comets and asteroids. But the diversity displayed by Oumuamua, Borisov, and Atlas suggests that our solar system may be just one example among many possible architectures for planetary systems. Some star systems may be metal-rich, producing rocky objects like Oumuamua. Others may be carbon-rich, creating bodies dominated by carbon monoxide and organic compounds like Borisov. Still others may be water-rich, generating objects like Atlas that carry vast reservoirs of H2O ice formed under conditions we can barely imagine. But the pattern extends beyond simple chemical composition. Each visitor has also displayed unique physical characteristics that speak to different formation mechanisms and evolutionary histories. Oumuamua's extreme elongation might result from tidal forces acting during a close encounter with a massive planet, or from the collision and merger of smaller objects under unusual gravitational conditions. Borisov's more conventional cometary nucleus suggests formation through the gradual accretion of ice and dust particles in a stable disk environment. Atlas's apparent internal differentiation implies processes that go beyond simple accretion, perhaps involving thermal evolution or chemical reorganization during its long interstellar journey. Even more intriguingly, the timing of these arrivals raises questions about whether their appearance in our solar system represents pure coincidence or something more systematic. 3 interstellar objects detected within a span of 8 years, after decades of searching that found nothing. Are we witnessing a statistical clustering, or has something changed about the interstellar environment that is directing more such objects toward our solar system? Some astronomers have suggested that our solar system's motion through the galaxy may be carrying us into a region of space with a higher density of interstellar debris. Others propose that improvements in our detection capabilities are finally allowing us to see objects that were always there, previously invisible against the background of stars. But a more intriguing possibility is that these objects represent the leading edge of a much larger population of interstellar wanderers, and that what we are witnessing is the beginning of a new phase in our understanding of the galaxy, its structure and dynamics. Perhaps interstellar objects are not rare visitors, but common threads weaving between star systems, carrying chemical information, and even the building blocks of planetary formation from one stellar neighborhood to another. Each new visitor adds another piece to a puzzle that spans the entire galaxy. They are teaching us that planetary systems are not isolated islands of matter orbiting their parent stars, but nodes in a vast network of chemical and physical exchange that connects every star to every other star through the slow traffic of wandering worlds. The pattern of the unknown is beginning to reveal itself, written in the diverse chemistry of objects that have traveled light years to reach us. And we are only beginning to decode what that pattern means for our understanding of our place in the cosmic community. In the vast darkness between stars, where space itself becomes a medium both empty and full of possibility, the birth of a wanderer like Atlas represents one of the most violent, yet beautiful processes in the galaxy. To understand what we are witnessing, we must journey backward through time, following the comet's trajectory not just through space, but through the deep history of stellar evolution and planetary destruction. The most likely scenario begins with a star system not unlike our own, but perhaps richer in heavy elements, blessed with the chemical legacy of previous generations of stellar death and rebirth. In this alien system, a family of planets formed from the gravitational collapse of a primordial disk, with giant worlds taking shape in the outer reaches where temperatures remained low enough for water to condense into solid form. Around these giant planets, in the gravitational shadows cast by their immense masses, smaller objects accumulated slowly over millions of years. Ice and rock and organic compounds, the detritus of planetary formation, gathered into loose confederations of debris that would eventually coalesce into comets and asteroids. Among these objects was the body that would one day become Atlas, growing slowly through the gentle accumulation of frozen water and trace compounds that carried the chemical signature of its birth nebula. But something went wrong in that distant system. Perhaps one of the giant planets migrated inward, its gravitational influence disrupting the delicate orbital architecture that had allowed small bodies to accumulate in stable regions. Perhaps a passing star approached too closely, its gravity reaching across interstellar distances to perturb the outer reaches of the planetary system. Or perhaps the star itself underwent some form of evolutionary crisis, a period of instability that changed its luminosity and radiation output, affecting the thermal balance of the entire system. Whatever the cause, the result was gravitational chaos. Objects that had orbited peacefully for millions of years found their paths suddenly altered, flung into new trajectories that carried them far from their points of origin. Some were scattered inward, where they collided with planets or fell into the central star. Others were ejected entirely, launched into the interstellar void with velocity sufficient to escape their star's gravitational embrace forever. Atlas was among those chosen for exile. The ejection itself would have been a moment of profound transformation. In the space of perhaps a few thousand years, a geological instant, the proto-comet transitioned from being a member of a stable planetary system to becoming a wanderer in the galactic night. Its surface temperature dropped to within a few degrees of absolute zero. Its chemical composition was locked into stasis, preserved in crystalline matrices that would remain unchanged for millions of years. But the statistics of such ejections are sobering. For every one interstellar object that finds its way into another star system, billions more wander forever in the space between stars, gradually cooling toward thermal equilibrium with the cosmic background radiation, becoming invisible ghosts carrying the chemical memory of worlds that no longer exist. The fact that we have detected 3 such objects in less than a decade suggests something remarkable about the frequency of these ejection events throughout the galaxy. Either planetary systems are far less stable than we previously imagined, or the processes that eject small bodies into interstellar space are more common and more efficient than theoretical models predict. Recent computer simulations have revealed that even minor perturbations in a planetary system's architecture can lead to the ejection of vast numbers of small bodies. The migration of a single giant planet, or the passage of a distant stellar companion, can destabilize entire populations of comets and asteroids, flinging them into interstellar space like cosmic buckshot fired from a gravitational slingshot. If these simulations are correct, the galaxy may be filled with trillions of such wanderers, a vast diaspora of small bodies carrying the chemical heritage of every planetary system that has ever experienced gravitational instability. Most will never encounter another star system, but a few by the statistics of chance, and the patient accumulation of probability over cosmic time will find their way into the gravitational embrace of foreign suns. The journey that brought Atlas to our solar system likely lasted millions of years, during which it traveled through regions of space where the very nature of matter and energy differ from our local environment. It passed through the heliospheres of other stars, where different stellar winds carried different chemical compositions. It drifted through molecular clouds where cosmic ray bombardment gradually altered its surface chemistry. It witnessed the birth and death of stars from distances that rendered them mere points of light against the cosmic background. And throughout that long journey, locked within its frozen heart, Atlas carried the water that now streams away from its nucleus as it approaches our sun. Water that condensed from vapor in the atmosphere of an alien world. Water that may have fallen as rain on continents we cannot imagine. Water that represents a direct physical connection between our solar system and a world that died before our Earth was born. The question of origin becomes not just a matter of astronomical curiosity, but a meditation on the deep connections that bind all matter in the universe. We are not isolated on our small world, separated from the rest of the galaxy by the immense distances between stars. We are part of a vast network of chemical exchange, connected to every other star system through the slow traffic of wandering bodies that carry between worlds the very substances from which planets and life are made. Or perhaps, as some astronomers have begun to whisper in the corridors of conferences and the margins of research papers, the odds aren't what we think they are at all. In the grand theater of stellar birth, where new suns ignite from the gravitational collapse of molecular clouds, a remarkable possibility emerges from the growing understanding of interstellar objects like Atlas. These wanderers may not be merely refugees from destroyed planetary systems, but essential actors in the drama of world formation itself. Consider the challenge faced by every newly forming star system. In the primordial disk of gas and dust that surrounds a young star, the process of planetary formation must overcome what astronomers call the meter barrier, a fundamental obstacle that prevents small particles from growing into the kilometer-sized objects that can eventually become planets and moons. Dust grains in these early disks can stick together through electrostatic forces to form pebbles, and pebbles can accumulate into boulders through gentle collisions. But when objects reach roughly 1 meter in size, they encounter a critical problem. They become large enough to feel significant drag from the surrounding gas, but not large enough to resist that drag through their own gravity. The result is a death spiral that carries meter-sized objects inward toward the central star, where they are vaporized long before they can grow into planetary building blocks. This meter barrier has puzzled astronomers for decades. Computer simulations of planetary formation consistently show that most solid material should be lost to the central star during the early phases of disk evolution. Yet we observe abundant rocky planets throughout the galaxy. Something must be providing a shortcut across the meter barrier, allowing planetary formation to proceed more efficiently than pure accretion models predict. Enter the possibility that interstellar objects like Atlas represent that shortcut. When a young star system captures wandering bodies from interstellar space, it gains ready-made building blocks that bypass the meter barrier entirely. These objects, already kilometers in size and held together by their own gravity, can serve as the seeds around which larger bodies accumulate. Instead of struggling to grow from dust grains to boulders to kilometers, planetary formation can begin with kilometer-sized cores that are already stable against gas drag and ready to accrete additional material. The process of capturing interstellar objects is not as rare as might be expected. Computer simulations show that young star systems, with their extended disks of gas and dust, can gravitationally capture significant numbers of passing bodies. The gas disk acts as a brake, slowing down interstellar wanderers enough for them to become permanently bound to their new stellar parent. Dr. Sean Raymond of the Laboratoire d'Astrophysique de Bordeaux has calculated that a typical young star system might capture thousands or even tens of thousands of interstellar objects during the first few million years of its existence. These captured bodies would then become incorporated into the growing planets, contributing both their mass and their exotic chemistry to the final worlds that emerge from the planetary formation process. The implications are profound for our understanding of planetary composition and the potential for life throughout the galaxy. If planets regularly incorporate interstellar materials during their formation, then every world is essentially a hybrid, built partly from local materials and partly from exotic matter that originated in other star systems. This cosmic cross-pollination could explain some of the chemical anomalies observed in meteorites and comets within our own solar system. Objects that show isotopic ratios inconsistent with formation from purely local materials might be the descendants of captured interstellar bodies, carrying within their structure the chemical fingerprints of alien star systems. Even more intriguingly, the process suggests that the building blocks of life itself might be shared between star systems through the medium of wandering comets and asteroids. If objects like Atlas carry complex organic compounds formed in other stellar environments, they could seed young planetary systems with the chemical precursors necessary for life to emerge. The water streaming from Atlas as it passes through our solar system represents a direct test of this hypothesis. The isotopic composition and chemical complexity of that water carries information about its formation environment, potentially revealing whether it originated in conditions similar to those found in our own outer solar system or in the more exotic environment of an alien star. But the seeding hypothesis extends beyond individual objects to entire populations of interstellar wanderers. If the galaxy is filled with trillions of such bodies, as recent observations suggest, then every star system is constantly sampling materials from throughout the galactic neighborhood. The formation of planets becomes not just a local process driven by conditions in a single stellar disk, but a galactic process that incorporates matter and chemistry from across the entire spiral arm. This perspective transforms our understanding of planetary diversity. Instead of expecting planets to reflect only the composition of their local star and nebula, we should expect them to show the integrated chemical signature of their entire galactic region. The diversity of exoplanets observed by space telescopes might reflect not just the diversity of stellar compositions, but the diversity of interstellar chemistry that has been incorporated into planetary systems through the capture and accretion of wandering bodies. Perhaps most remarkably, this process suggests that every planet, including Earth, began as a stranger. The building blocks of our own world may have originated not in the solar nebula, but in the depths of interstellar space, as fragments of alien worlds that were captured and incorporated into the growing planets of our young solar system. The possibility casts our relationship with objects like Atlas in an entirely new light. We are not observing foreign visitors from distant realms, but potential relatives, carriers of materials that may be chemically related to the very substances from which our own world was built. Every molecule of water streaming from the comet's nucleus might be a cousin to the water in our oceans, separated by space and time but united by the deep chemical processes that connect all matter in the galaxy. In this view, the universe becomes not a collection of isolated star systems, each developing in chemical isolation, but a vast network of interconnected chemistry where the building blocks of worlds flow freely between stellar neighborhoods, carried by messengers like Atlas across the patient darkness of interstellar space. We are all made of star stuff, as Carl Sagan observed, but we may also be made of the stuff of many stars, brought together by the wandering chemistry of interstellar space. The revelation that interstellar objects might serve as planetary building blocks opens a new chapter in our understanding of how worlds are born. In this cosmic factory, the assembly line extends not just across the few astronomical units of a single star system, but across the light years of interstellar space, drawing materials from throughout the galaxy to construct the planets we observe around distant suns. The traditional model of planetary formation paints a picture of worlds growing slowly from the ground up, beginning with microscopic dust grains that stick together through electrostatic forces to form ever larger aggregates. In this scenario, planets are purely local constructions, built entirely from materials that condensed from the disk of gas and dust surrounding their parent star. But this bottom-up approach faces fundamental challenges that have puzzled astronomers for decades. The journey from dust grain to planet requires crossing several critical size thresholds, each presenting its own obstacles to continued growth. The meter barrier represents just one of these challenges. Others exist at different scales throughout the accretion process. At the centimeter scale, dust aggregates become fragile and prone to disruption during collisions. At the kilometer scale, gravitational focusing begins to dominate the accretion process, but objects must first survive long enough in the hostile disk environment to reach this size. At the planetary embryo scale, dozens of moon-sized bodies must somehow avoid destroying each other through catastrophic collisions long enough to merge into fully formed planets. Each of these barriers represents a bottleneck that should dramatically slow planetary formation. Yet observations of young star systems show that planets form readily and rapidly, often within just a few million years of stellar birth. The efficiency of observed planetary formation suggests that some mechanism must be accelerating the process beyond what pure accretion models predict. The injection of ready-made kilometer-sized bodies from interstellar space provides exactly such a mechanism. These objects arrive pre-assembled, having already overcome the major barriers to planetary growth in their original star systems. When captured by a young stellar disk, they can immediately begin serving as gravitational seeds around which additional material accumulates. Computer simulations of this hybrid formation process reveal remarkable efficiency gains compared to pure local accretion. Systems that incorporate captured interstellar bodies can form planets up to 10 times faster than those relying solely on local materials. The interstellar objects serve as nucleation sites that catalyze planetary growth, much like seed crystals accelerate the formation of larger crystals in supersaturated solutions. But the benefits extend beyond simple acceleration of the formation process. Interstellar objects also introduce chemical diversity that would be impossible to achieve through purely local accretion. Each captured body carries the isotopic and elemental signature of its birth environment, potentially representing stellar conditions very different from those found in the host system. This chemical cross-pollination could explain some of the remarkable diversity observed in exoplanet compositions. Planets orbiting metal-poor stars sometimes show surprisingly high abundances of heavy elements, while planets around metal-rich stars occasionally display compositions, suggesting formation from unusually primitive materials. The incorporation of interstellar bodies during planetary formation could account for these compositional anomalies. The process also provides a natural explanation for the presence of water and organic compounds in planetary systems, where such materials should be rare. Stars that form in regions of the galaxy with low water abundance could still produce water-rich planets if they capture sufficient numbers of ice-rich interstellar objects during their youth. The chemical heritage of planets becomes not just a reflection of their immediate stellar environment, but an integration of materials drawn from across their galactic neighborhood. Perhaps most intriguingly, the hybrid formation model suggests that the basic architecture of planetary systems, the number sizes and orbital arrangements of planets, might be influenced by the population of interstellar objects available for capture during the formation epoch. Systems that form in regions of high interstellar object density might produce different planetary architectures than those forming in regions where such objects are rare. This introduces a new variable into the equation of planetary formation: the galactic environment. The same stellar disk might produce very different planetary systems depending on its location within the galaxy, its motion through regions of varying interstellar object density, and the timing of its formation relative to events that might populate nearby space with wandering bodies. The implications extend to the search for life throughout the galaxy. If the building blocks of life are regularly transported between star systems by interstellar objects, then the potential for biological development becomes less dependent on the local conditions around individual stars and more dependent on the integrated chemical history of entire galactic regions. Regions of the galaxy that have experienced high rates of stellar formation and planetary system disruption might be enriched in organic-rich interstellar objects, creating favorable conditions for life to emerge in subsequently forming planetary systems. Conversely, regions with lower rates of stellar evolution might produce planets with less diverse chemistry, potentially limiting the pathways available for biological development. The cosmic factory of planetary formation emerges as a process that operates on multiple scales simultaneously, from the local physics of dust grain collisions to the galactic dynamics of stellar motion and chemical evolution. Planets are not simply local constructions, but galactic collaborations, built from materials contributed by multiple star systems across cosmic time. In this view, every world becomes a museum of galactic history, its composition telling the story not just of its own formation, but of the chemical evolution of its entire stellar neighborhood. The water in our oceans, the carbon in our bodies, the metals in our technology, all might carry within their atomic structure the signatures of processes that occurred around distant stars, delivered to our forming Earth by messengers like Atlas that wandered the galactic night for millions of years before finding their way to our solar system. And if this process has been operating throughout the galaxy's history, then the building blocks of Earth-like worlds are constantly in motion, carried by the patient traffic of interstellar objects from the debris of dead worlds to the nurseries of worlds yet to be born. In the computer laboratories of astronomical research institutions around the world, sophisticated simulations paint a picture of cosmic choreography that challenges our most basic assumptions about the isolation of stellar systems. These numerical experiments reveal that the capture of interstellar objects by young star systems may not be a rare occurrence, but rather a fundamental process that shapes the formation and evolution of planetary systems throughout the galaxy. The key to understanding this process lies in the extended structure of protoplanetary disks, those vast wheels of gas and dust that surround newly formed stars like cosmic gardens, where planets slowly grow from seed to maturity. These disks are far larger and more diffuse than the compact planetary systems they eventually produce. Extending outward for hundreds of astronomical units, and containing enough material to gravitationally influence objects passing through the surrounding interstellar medium. When an interstellar wanderer like Atlas encounters such a disk, it experiences something akin to atmospheric drag, but operating on a scale that dwarfs anything we experience on Earth. The tenuous gas that fills the outer regions of the disk exerts a subtle but persistent force on passing objects, gradually robbing them of the kinetic energy that would otherwise carry them back into interstellar space. Dr. Alan Jackson of the Center for Planetary Sciences at the University of Toronto has conducted extensive simulations of this capture process, revealing that young star systems can be remarkably efficient at snaring interstellar visitors. His model suggests that a typical protoplanetary disk might capture several hundred interstellar objects during the first million years of its existence, with the most massive systems potentially capturing thousands. The efficiency of the capture process depends on several factors that vary from system to system. Larger, more massive disks present bigger targets and exert stronger gravitational influences on passing objects. Denser disks provide more effective drag forces that can slow down potential captives. And systems located in regions of high interstellar object density, perhaps near the sites of recent stellar formations or planetary system disruptions, have more opportunities for capture events. But the simulations reveal something even more remarkable. The capture process is highly selective, preferentially snaring objects with specific size ranges and composition profiles. Very small objects lack sufficient cross-sectional area to experience significant drag forces, while very large objects carry too much kinetic energy to be effectively slowed down by disk interactions. The sweet spot for capture lies in the size range of typical comets and asteroids, objects a few kilometers across, exactly like Atlas. This size selectivity has profound implications for the chemical evolution of planetary systems. The captured objects represent a curated sample of interstellar material, filtered by the physics of gas drag and gravitational capture, to include primarily those bodies most likely to contribute constructively to planetary formation processes. Moreover, the timing of capture events introduces another layer of selectivity. Objects captured early in a system's evolution become incorporated into the growing planets themselves, contributing their exotic chemistry to the final composition of the worlds that emerge from the formation process. Objects captured later, after the planets have largely formed, remain as distinct bodies in the outer reaches of the system, comets and asteroids that preserve their interstellar heritage largely intact. This temporal distinction suggests that every mature planetary system should contain two distinct populations of small bodies, those that formed locally from the original disk material, and those that represent captured interstellar immigrants. The native population should show chemical compositions consistent with formation from local materials, while the immigrant population should display the diverse signatures of formation around different stars under different conditions. Recent observations of small bodies in our own solar system have begun to reveal hints of this predicted dichotomy. Some asteroids and comets show isotopic ratios and chemical compositions that are difficult to explain through formation from purely local materials. These compositional anomalies might represent the descendants of interstellar objects captured during the early history of our solar system. The capture hypothesis also provides a natural explanation for some of the architectural diversity observed in exoplanetary systems. Systems that captured large numbers of interstellar objects during their formation might develop different planetary arrangements than those that relied primarily on local materials. The gravitational influence of captured bodies could alter the orbital evolution of growing planets, leading to different final configurations. Perhaps most intriguingly, the process suggests that stellar systems are not gravitationally isolated entities, but rather nodes in a vast network of material exchange that operates throughout the galaxy. Every star system both contributes to and receives from this galactic recycling program, ejecting some of its own small bodies into interstellar space while capturing wanderers from other systems. The scale of this exchange network is staggering. If typical star systems both eject and capture thousands of small bodies during their lifetimes, and if the galaxy contains hundreds of billions of star systems, then the space between stars must be filled with trillions of wandering objects carrying chemical information between stellar neighborhoods. This perspective transforms our understanding of galactic chemical evolution. Instead of viewing each star system as an isolated chemical laboratory developing according to its own local conditions, we must consider the possibility that chemical information flows freely between systems through the medium of captured interstellar objects. The composition of planets becomes not just a reflection of their local stellar environment, but an integration of chemical signatures drawn from across their galactic neighborhood. Stars are not alone in creating their worlds. They borrow, trade, and inherit materials from throughout their corner of the galaxy, weaving together the chemical heritage of multiple stellar generations into the worlds that orbit around them. The planetary systems we observe today are not pure local constructions, but collaborative efforts that incorporate the contributions of countless other stars, delivered by messengers that have crossed the vast emptiness of interstellar space to participate in the ancient dance of world formation. In this cosmic marketplace of chemistry and construction materials, every planet becomes a multicultural creation, built from ingredients contributed by a diverse community of stellar systems across the galaxy, and objects like Atlas serve as the cargo ships of this interstellar commerce, carrying precious chemical freight from the debris of distant worlds to the construction sites of worlds yet to be born. Two hydrogen atoms bonded to one oxygen atom in a molecular arrangement so simple it can be drawn by a child, yet so fundamental to existence that its presence transforms barren rock into the potential for life itself. As Atlas streams its cargo of H2O molecules into the vacuum of space, it carries with it not just the chemistry of another world, but perhaps the very ingredient that makes worlds capable of supporting the emergence of biology. The significance of detecting water in interstellar objects extends far beyond astronomical curiosity. Water serves as what chemists call a universal solvent, a medium in which the complex chemical reactions necessary for life can occur with the fluidity and flexibility that biological processes require. Without liquid water, the delicate dance of molecular interactions that underlies metabolism, reproduction, and evolution becomes essentially impossible. But water's role in the story of life goes deeper than its function as a biological solvent. The molecule itself participates directly in many of the chemical reactions that sustain living systems. Photosynthesis splits water molecules to provide the hydrogen atoms needed for sugar synthesis. Cellular respiration combines oxygen with organic molecules to release energy, producing water as a byproduct. The constant cycling of water through biological systems drives much of the chemistry that makes life possible. When we observe water streaming from Atlas, we are witnessing the dispersal of this life-enabling molecule from one corner of the galaxy to another. Every H2O molecule carried in the comet's tail represents a potential participant in biological processes that might unfold on worlds we cannot imagine, around stars whose light we may never see. The isotopic composition of Atlas's water provides crucial clues about the conditions under which this life ingredient formed. Different ratios of deuterium to hydrogen or of different oxygen isotopes tell the story of the temperature, pressure, and chemical environment that existed when the water first condensed from vapor to solid in the outer reaches of an alien star system. Water. Preliminary analysis suggests that Atlas is water formed under conditions subtly different from those found in our own outer solar system. The deuterium to hydrogen ratio is slightly elevated compared to Earth's oceans, suggesting formation in an environment that was either colder or more chemically reducing than the region where Earth's water originated. This difference, small though it may be, provides a direct link to the physical conditions that existed around another star billions of years ago. But the implications extend beyond the specific chemistry of water formation. If interstellar objects like Atlas regularly transport water between star systems, they create the possibility for biological ingredients to be shared across vast regions of the galaxy. The water in Earth's oceans might include molecules that originated around distant stars, delivered by ancient impacts of interstellar comets that arrived during our planet's youth. This cosmic sharing of biological ingredients could help explain one of the great puzzles of astrobiology, the apparent rapid emergence of life on Earth. Traditional models of life's origin assume that all the necessary chemical precursors had to be synthesized locally from the raw materials available in Earth's early environment. But if Earth was seeded with complex organic compounds and water from interstellar sources, the chemical foundations for life might have been delivered ready-made from the broader galactic community. The possibility gained support from the growing understanding of organic chemistry in space. Interstellar clouds contain complex molecules, including amino acids, sugars, and other compounds that serve as building blocks for biological systems. If these molecules can survive the journey between star systems embedded in the icy matrices of objects like Atlas, they provide a mechanism for distributing the chemical precursors of life throughout the galaxy. Dr. Jennifer Eigenbrod of NASA's Goddard Space Flight Center has described this process as galactic panspermia, not the transfer of living organisms between worlds, but the transfer of the chemical ingredients from which life can emerge. In this view, the galaxy becomes a vast chemical laboratory, where the products of stellar nucleosynthesis and interstellar chemistry are constantly mixed and redistributed by the wandering traffic of comets and asteroids. The water streaming from Atlas participates in this grand redistribution. Every molecule that escapes the comet's gravitational grasp becomes part of the interplanetary medium, potentially available for incorporation into the formation of new worlds or the evolution of existing ones. Some will be captured by the solar wind and carried to the outer reaches of the solar system. Others will be swept up by planets and moons, adding their alien chemistry to the inventory of materials available for geological and perhaps biological processes. The process operates with the patience of geological time and the persistence of physical law. Over millions of years, the accumulated contributions of interstellar objects could significantly alter the chemical composition of planetary systems, enriching them with materials and compounds that originated under very different conditions around very different stars. Perhaps most poetically, this cosmic recycling of water connects every drop of liquid on Earth to a vast network of chemical heritage that spans the galaxy. The water in our bodies, the water that falls as rain, the water that fills our oceans, all of it participates in a chemical lineage that extends back through the birth and death of countless stars, connected by the patient wandering of objects like Atlas across the emptiness of interstellar space. If the water streaming from this alien comet once touched the surface of worlds we cannot imagine, if it once participated in chemical processes under foreign skies, then in a very real sense, every molecule of water on Earth carries within its atomic structure a connection to places and processes that transcend our local experience. We are not isolated on our small world, but participants in a galactic community of chemistry that has been billions of years in the making. The life ingredient flows between worlds on currents of gravity and time, carried by messengers like Atlas that cross the vast darkness between stars to deliver the chemical gifts that make biology possible. And in that flowing, that constant exchange of the molecules that make life possible, we find perhaps the deepest connection between our world and the cosmos that surrounds us. Deep within the frozen heart of Atlas, something burns. Not the familiar fire of chemical combustion, but a more subtle form of energy release that challenges our understanding of how objects behave in the frigid realm beyond the outer planets. The comet's extraordinary level of water emission at such vast distances from the Sun suggests internal processes that operate according to principles extending far beyond simple solar heating. At its current distance from our star, Atlas receives less than 1% of the solar energy that reaches Earth. By conventional physics, this meager energy input should barely be sufficient to sublimate surface ice, much less drive the massive water emissions that Swift Observatory has detected. Yet the comet continues to hemorrhage water vapor at rates that would be remarkable even for objects much closer to the Sun. The discrepancy points to something fundamental happening within the comet's interior, a source of energy that operates independently of external solar heating. Several possibilities emerge from the physics of ice and the chemistry of interstellar materials, each suggesting that Atlas may be powered by forces locked within its own crystalline structure. The most likely explanation involves the slow crystallization of amorphous ice deep within the comet's core. When water vapor condenses rapidly under the extreme conditions of interstellar space, it often forms in an amorphous state, essentially frozen water that lacks the organized crystal structure of normal ice. This amorphous ice exists in a state of stored energy, like a compressed spring waiting to be released. As Atlas approaches the Sun and begins to warm even slightly, this metastable ice undergoes a phase transition, reorganizing itself into more stable crystalline forms. The transition releases latent heat, energy that was stored in the disordered molecular bonds of the amorphous phase, and is now liberated as the molecules reorganize themselves into more efficient arrangements. The amount of energy available from this crystallization process is substantial. Laboratory experiments suggest that the phase transition from amorphous to crystalline ice can release enough thermal energy to drive significant sublimation, creating a self-sustaining process where crystallization-induced heating drives water emission, while the loss of water vapor allows deeper layers of amorphous ice to warm and undergo their own phase transitions. But crystallization may not be the only internal energy source at work. Atlas has been exposed to cosmic ray bombardment throughout its millions-year journey through interstellar space. These high-energy particles gradually alter the chemical structure of materials they encounter, breaking molecular bonds and creating new compounds in a process called radiolysis. The energy deposited by cosmic ray impacts accumulates over time, stored in the form of chemical bonds that are thermodynamically unstable but kinetically trapped at low temperatures. As the comet warms during its approach to the Sun, these stored chemical changes can begin to reverse, releasing the energy that was deposited by cosmic ray impacts over geological timescales. Dr. Murthy Gudapati of NASA's Jet Propulsion Laboratory has studied similar processes in laboratory analogs of interstellar ice, revealing that cosmic ray processing can create what he calls chemical batteries, molecular arrangements that store energy for millions of years before releasing it when triggered by modest temperature increases. If Atlas contains such chemical batteries, distributed throughout its interior, they could provide a distributed heat source that operates independently of solar heating. The comet would essentially be powered by the accumulated energy of cosmic ray impacts that occurred during its long journey through the galactic night. Even more exotic possibilities emerge from the extreme conditions that exist in the cores of large comets. At the center of a kilometers-wide object, pressures can reach levels comparable to those found deep within planetary interiors. Under such conditions, water ice can assume crystalline forms that don't exist at surface pressures, creating materials with different thermal and mechanical properties than ordinary ice. These high-pressure ice phases may be metastable at the lower pressures found near the comet's surface, potentially releasing energy as they decompress and transform into more familiar forms of ice. The process could create convective currents within the comet's interior, transporting heat from deep within the nucleus to surface regions where it drives sublimation. The implications of internal heating extend beyond the behavior of individual comets to fundamental questions about the structure and evolution of interstellar objects. If wandering bodies like Atlas carry within their cores stores of energy, accumulated over millions of years of cosmic evolution, they become more than passive chunks of ice and rock. They become active systems, capable of supporting complex internal processes that can operate for vast periods of time without external energy input. This perspective transforms our understanding of what it means for an object to be active in the astronomical sense. Activity need not require proximity to a star or the input of external energy. Objects can carry within themselves the capacity for long-term evolution and change, powered by energy sources that operate on timescales comparable to the age of planetary systems themselves. Perhaps most intriguingly, the internal heating of interstellar objects creates the possibility for chemical evolution to continue during their long journeys between stars. If the interiors of objects like Atlas can remain warm enough to support liquid water, even briefly, they become mobile chemical laboratories where complex reactions can occur in the isolation of interstellar space. The water streaming from Atlas may therefore represent not just the sublimation of ancient ice, but the products of chemical processes that occurred within the comet's interior during its million-year journey to our solar system. We may be witnessing the emergence of compounds that formed in the mobile chemistry of interstellar space, created by processes that have no equivalent in the static environments of planetary surfaces. Something is warming Atlas from within. Whether that something is crystallization, cosmic ray chemistry, pressure-induced phase transitions, or processes we have yet to imagine, it speaks to a universe far more dynamic and chemically active than our earthbound experience might suggest. The comet carries within its frozen heart not just the memory of another world, but the ongoing expression of forces that operate in the space between worlds, writing their stories in molecular bonds that span the galaxy. What if the fire we see streaming from Atlas isn't sunlight at all, but memory? The accumulated thermal history of a million-year journey, finally finding expression as the comet encounters the gentle warmth of our distant sun. In the autumn of 2017, when the elongated object we now call Oumuamua first tumbled through our solar system, it sparked a different kind of speculation that reached far beyond conventional astronomy. Dr. Avi Loeb, chairman of Harvard's astronomy department, suggested with the careful language of scientific inquiry that the object's unusual properties might warrant consideration of artificial origins, not natural formation around a distant star, but deliberate construction by an intelligence we could not fathom. The suggestion sent ripples through both the scientific community and the public imagination. Here was a respected astronomer, publishing in peer-reviewed journals, seriously considering the possibility that we had witnessed our first encounter with technology from another civilization. The object's extreme elongation, its unusual acceleration pattern, its lack of detectable water emissions despite clear evidence of some form of outgassing. All of these characteristics, Loeb argued, were more consistent with an artificial origin than with any known natural process. The response from the broader astronomical community was swift and decisive. Alternative explanations emerged for each of Oumuamua's unusual properties. The elongation could result from tidal stretching during a close encounter with a massive planet. The acceleration could be explained by outgassing of hydrogen gas, too diffuse to detect but sufficient to provide the observed thrust. The lack of water could simply reflect formation in the inner regions of its birth system, where higher temperatures would have prevented the accumulation of volatile ices. Yet Loeb's speculation, controversial though it was, touched on something profound about human nature and our relationship with the cosmos. When confronted with phenomena that challenge our understanding, we inevitably seek patterns that might reveal intention, design, purpose. The search for extraterrestrial intelligence represents one of the most fundamental questions we can ask about our place in the universe. Are we alone? Now, with Atlas demonstrating its own unusual properties, the massive water emissions, the internal heating, the complex chemical signatures, we might be tempted to ask similar questions. Could such extraordinary behavior indicate something beyond natural processes? Could the timing of these interstellar visitors, 3 objects in 8 years after decades of finding none, suggest something more than statistical coincidence? But the true wonder of Atlas lies not in speculation about artificial origins, but in the revelation of just how sophisticated natural processes can be. The comet's behavior, extraordinary though it may seem, emerges from the interplay of physics and chemistry operating under conditions that push the boundaries of our Earth-based experience. It represents nature's own form of engineering, crafted by forces that operate on scales of time and space that dwarf human comprehension. The internal heating that drives Atlas' water emissions demonstrates chemistry that spans millions of years in interstellar distances. The energy now being released was stored during cosmic ray bombardment that occurred during the comet's journey through the galactic night. The crystallization processes occurring within its core represent phase transitions that were initiated when the object first formed around an alien star, then suspended in the deep freeze of interstellar space, until triggered by the gentle warming of our own sun. This is engineering on a cosmic scale, but it is the engineering of natural law rather than conscious design. The forces that shaped Atlas operated with the patience of geological time and the precision of physical law, creating an object whose behavior challenges our preconceptions about what is possible in the natural world. The human tendency to seek signals in the noise, to look for patterns that might reveal intelligence behind apparent randomness, reflects our deep need to find meaning in the cosmos. Every unexplained phenomenon becomes a potential message, every anomaly a possible sign that we are not alone in our capacity for thought and creation. But the universe has its own intelligence, not conscious in the way we understand consciousness, but sophisticated in its capacity to create complexity from simplicity, to generate behaviors that appear designed yet emerge from the blind operation of natural forces. The intelligence we seek in the signals from space may be all around us, expressed in the exquisite complexity of natural processes that operate according to principles we are only beginning to understand. Atlas carries its own message, written not in the deliberate symbols of conscious communication, but in the universal language of chemistry and physics. It speaks of formation processes that operated around distant stars, of journey conditions that exist in the space between worlds, of energy storage and release mechanisms that span millions of years of cosmic evolution. The signal that Atlas broadcasts is not artificial, but it is no less profound for being natural. It tells us that the universe is far more creative, far more capable of generating surprising and beautiful phenomena than our limited experience might suggest. It reveals that intelligence need not be conscious to be profound, that complexity need not be designed to be meaningful. In seeking signals from other civilizations, we sometimes overlook the signals that surround us constantly. The messages written in the behavior of natural systems, the information encoded in the chemistry of objects that have traveled across the galaxy to reach us. These signals may not indicate the presence of other minds like our own, but they reveal something equally remarkable. A universe that is itself a kind of intelligence, capable of creating wonders that exceed our capacity to fully comprehend them. The wonder of Atlas lies not in the possibility that it represents alien technology, but in the certainty that it represents the universe's own form of engineering, a natural intelligence that operates on scales of space and time, that humble our most ambitious projects, creating beauty and complexity through the patient application of physical law across cosmic distances and geological time. In the streaming water vapor that trails behind Atlas like a ghostly banner, we find an unexpected reflection of our own condition. Two objects separated by billions of years and countless light years, yet united by the fundamental act of releasing pieces of themselves into the void, seeking some form of connection with the vastness that surrounds them. Consider the parallel. Atlas hemorrhages water molecules into the emptiness between worlds, each H2O molecule carrying within its bonds the chemical memory of an alien star system. We, in our own way, broadcast signals into that same emptiness, radio waves carrying music and mathematics and the accumulated hopes of human civilization, each transmission carrying within its modulated frequencies the cultural memory of our own small world. Both processes represent a form of dispersal, a scattering of essence into the cosmic dark in patterns that speak of origin and intention, even when no conscious intention may exist. The comet cannot choose to release its water any more than we can choose to stop broadcasting our electromagnetic signature into space. Both are expressions of deeper forces, physics in the case of Atlas, consciousness, and culture in our own case, that compel the sharing of information across the barriers of space and time. The image becomes even more poetic when we consider the temporal scales involved. Atlas has been journeying toward this moment of dispersal for millions of years, carrying its cargo of alien water across distances that reduce our largest imaginings to insignificance. We have been broadcasting our signals for less than a century, yet both represent the same fundamental impulse: the transformation of internal content into external expression, the conversion of stored information into transmitted message. But the mirroring extends beyond simple parallel behavior, to touch something deeper about the nature of existence in a universe that seems designed to scatter rather than to gather, to disperse rather than to concentrate. Both human civilization and interstellar comets exist as temporary concentrations of complexity in a cosmos that tends toward increasing entropy, increasing randomness, increasing dispersal of organized structures into simpler, more distributed forms. The second law of thermodynamics suggests that all organized systems must eventually disperse their energy and information into the background noise of the universe. Yet both Atlas and human civilization represent rebellion against this tendency. Islands of organized complexity that persist for brief moments against the tide of cosmic entropy, sharing their organized information with the cosmos before that organization inevitably dissolves. In this light, the water streaming from Atlas becomes more than simple sublimation. It becomes a form of communication, a way for the organized chemistry of one world to share its information with the broader galactic community. Each molecule carries data about temperature, pressure, isotopic ratios, and chemical processes that occurred under alien conditions. The comet is broadcasting its autobiography in the universal language of molecular structure, telling the story of its birth and journey to anyone with the instruments to listen. We do something remarkably similar when we launch space probes carrying golden records, or when we encode messages in our radio transmissions, or even when we simply live our lives in ways that leave traces of our existence for future discovery. We are broadcasting our own autobiography in the languages of technology and culture, sharing the information that defines our existence with a universe that may or may not contain listeners. The parallel suggests something profound about the relationship between consciousness and cosmology. Perhaps the tendency to broadcast information, to share organized complexity with the surrounding environment, represents a fundamental principle that operates at multiple scales throughout the universe. Perhaps consciousness itself is simply one expression of a deeper cosmic tendency toward information sharing and communication. At the molecular level, Atlas demonstrates this principle through chemistry. The sharing of electrons, the formation and breaking of bonds, the reorganization of matter according to principles that maximize information transfer between different chemical systems. At the biological level, life demonstrates it through reproduction, evolution, and the constant exchange of genetic information that drives the development of increasing complexity. At the cultural level, consciousness demonstrates it through language, art, science, and technology, all forms of information sharing that allow individual minds to communicate with other minds across the barriers of space and time. Viewed from this perspective, the encounter between Atlas and our solar system becomes more than an astronomical event. It becomes a moment of communication between two information processing systems operating on vastly different scales. The chemistry of an interstellar comet and the consciousness of a technological civilization, each broadcasting its own form of organized information into the cosmic medium that connects all things. The water molecules streaming from Atlas will eventually disperse throughout the solar system, some captured by planets and moons, others swept into interstellar space by the solar wind. In a similar way, our radio signals will eventually disperse throughout the galaxy, some perhaps captured by listening civilizations, others lost in the background radiation that fills the space between stars. Both represent the transformation of organized information into transmitted message, the conversion of stored complexity into shared communication. In watching Atlas release its ancient water into space, we observe a process that mirrors our own deepest impulses, the need to share what we are with what surrounds us, to convert our internal essence into external expression, to participate in the vast conversation that may be occurring throughout the cosmos at scales we are only beginning to perceive. We are all in our own ways, leaking into space, dispersing the organized information that defines our existence into the medium that connects us to everything else that exists. The cosmic mirror shows us not alien visitors, but fellow participants in the universe's tendency toward communication, toward the sharing of organized complexity across the vast distances that separate one island of information from another, both seeking connection, both broadcasting messages, both temporary concentrations of organized information in a universe that tends toward dispersal, yet somehow manages to create beauty in that very act of scattering what was once gathered, of sharing what was once contained, of communicating what was once isolated. 8 years. In the vast context of cosmic time, where stellar evolution unfolds over billions of years and galactic rotation occurs over hundreds of millions, 8 years represents barely a whisper, scarcely a heartbeat in the life of the universe. Yet within this brief span, our understanding of interstellar objects has been revolutionized by the arrival of 3 messengers from the depths of space, each carrying its own secrets, each rewriting our assumptions about the nature of matter and motion in the galaxy. October 19, 2017. The Panoramic Survey Telescope and Rapid Response System at Haleakala Observatory in Hawaii detects an object moving with unusual speed across the stellar background. Initially cataloged as an asteroid, then reclassified as a comet when no coma is detected, 1I Oumuamua ultimately defies both categories. Its hyperbolic trajectory confirms what astronomers had long theorized but never observed. We are witnessing our first confirmed visitor from another star system. The object's behavior proves as enigmatic as its origin. Elongated to an extreme degree, tumbling end over end like a cosmic cigarette, it displays no detectable water emissions, yet shows clear evidence of non-gravitational acceleration as it sweeps around the Sun and heads back toward interstellar space. Attempts to image it reveal only a point of reflected light, too distant and too small to resolve surface features. Yet its unusual properties spark speculation that ranges from exotic ice compositions to theories of artificial origin. Oumuamua departs as mysteriously as it arrived, accelerating away from our solar system on a trajectory that will carry it into the constellation Pegasus, where it will fade below the detection limits of our most sensitive instruments and become once again a silent wanderer in the galactic night. Its brief passage leaves behind more questions than answers, but also the tantalizing certainty that such objects exist, that the galaxy is filled with wanderers carrying the chemical and physical signatures of alien star systems. August 30th, 2019. Gennady Borisov, an amateur astronomer operating a small telescope from his observatory in Crimea, notices an object that doesn't belong in his catalog of known asteroids and comets. Follow-up observations reveal another hyperbolic trajectory, another visitor from interstellar space, but this time one that behaves more like the comets we know. 2I Borisov develops a prominent coma and tail as it approaches the Sun, displaying the familiar signs of ice sublimation driven by solar heating. But spectroscopic analysis reveals a composition dominated by carbon monoxide rather than water, a chemical signature that speaks of formation in the extremely cold outer reaches of its birth system, where temperatures were low enough for CO to condense into solid form. Its nucleus appears more loosely bound than typical solar system comets, gradually fragmenting as it rounds the Sun and heads back toward the cosmic dark. Unlike Oumuamua, Borisov offers astronomers multiple opportunities for detailed observation. Telescopes around the world track its progress, measuring its composition, structure, and behavior with unprecedented precision. The object becomes a Rosetta Stone for understanding the diversity of chemical environments that exist around other stars, providing direct evidence that planetary formation occurs under conditions very different from those found in our own solar system. July 2025. The third act in this cosmic drama begins with observations from NASA's Swift Observatory, revealing an object that defies the patterns established by its predecessors. 3I Atlas demonstrates water emissions on a scale that challenges our understanding of cometary physics, hemorrhaging H2O vapor, at rates that suggest internal processes extending far beyond simple solar heating. Unlike Oumuamua's mysterious dryness or Borisov's carbon monoxide dominance, Atlas appears to be a water world in miniature, carrying within its structure vast reservoirs of H2O ice that may have formed under conditions similar to those found in our own outer solar system. Yet its behavior suggests internal complexity that exceeds anything seen in native comets, with activity levels that imply energy sources operating independently of external solar input. 3 visitors, 3 completely different stories written in the universal languages of chemistry and physics. Each object arrives carrying the chemical fingerprint of its birth environment, yet each fingerprint tells a different tale about the diversity of conditions that exist throughout the galaxy. Oumuamua spoke of dry, rocky environments where water never condensed, where planetary formation occurred under high-temperature conditions that favored the accretion of metal and silicate compounds. Borisov told of cold, carbon-rich regions where organic chemistry flourished in the deep freeze of the outer nebula, where complex molecules could form and survive in crystalline matrices of frozen gas. Atlas carries the signature of water-rich environments not unlike our own outer solar system, yet with internal architecture that suggests thermal and chemical evolution during its long interstellar journey. The progression reveals something profound about the galaxy we inhabit. Far from being a uniform distribution of similar star systems, the Milky Way appears to be a vast laboratory where planetary formation experiments unfold under an enormous range of different conditions. Each stellar environment produces its own unique population of small bodies, each carrying the chemical signature of its specific formation conditions. The statistical improbability of detecting 3 such objects in less than a decade, after centuries of finding none, suggests that we have crossed a threshold in our observational capabilities. The universe has not suddenly begun sending us more interstellar visitors. Rather, we have finally developed the technology and techniques necessary to recognize them when they arrive. But the timing also raises deeper questions. Are we witnessing the beginning of a new epoch in astronomy, when interstellar objects become routine rather than extraordinary? Will the next decade bring dozens of such visitors, each adding new chapters to our understanding of galactic diversity? Or do these three objects represent a statistical clustering, an unlikely coincidence that may not be repeated for generations? Three visitors, each stranger than the last, each carrying within its structure the accumulated secrets of stellar environments we will never visit, chemical processes we can barely imagine, and formation conditions that extend the boundaries of what we thought possible in the universe of planetary systems. The timeline of visitors has only just begun, but already it suggests that we inhabit a galaxy far richer in diversity, far more complex in its chemistry, and far more surprising in its capacity to generate unexpected phenomena than our earthbound experience might suggest. We are not alone in the cosmos, not because of the presence of other conscious beings, but because we are part of a vast community of chemistry that connects every star system to every other, through the patient wandering of objects that carry between worlds the very substances from which planets and life are made. In the deepest recesses of Atlas, where pressures climb toward values that exist nowhere on Earth, the surface and temperatures hover just above the absolute zero of interstellar space, something burns with a fire that has been millions of years in the making. This is not the familiar flame of chemical combustion, but something far more subtle and far more patient. The slow release of energy that was stored in molecular bonds when the comet first formed around an alien star and has waited through eons of cosmic wandering for the moment of its release. The conventional models of cometary behavior, developed from decades of studying objects native to our own solar system, paint a picture of passive ice responding predictably to external heating. As a comet approaches the sun, increasing solar radiation warms its surface, causing water ice to sublimate directly from solid to gas. The process follows well-understood thermodynamics, with sublimation rates that correlate directly with distance from the sun and the intensity of received solar energy. Atlas defies these comfortable assumptions with behavior that suggests internal complexity, extending far beyond the scope of traditional models. Heat flow calculations based on the comet's observed emission rates indicate thermal processes occurring deep within its core, driven by energy sources that operate independently of external solar input. The object appears to be powered from within by fires that burn according to principles of physics and chemistry that push the boundaries of our terrestrial experience. The most likely source of this internal energy lies in the slow crystallization of amorphous water ice that has been locked in metastable configuration for millions of years. When water vapor condenses under the extreme conditions of interstellar space, temperatures approaching absolute zero, pressures lower than the best vacuum achievable in terrestrial laboratories, it often assumes an amorphous structure that lacks the organized crystal lattice of normal ice. This amorphous ice exists in a state of stored potential energy, like a compressed spring held in place by the extreme cold of the interstellar medium. The disordered arrangement of water molecules represents a higher energy state than the crystalline forms that ice assumes under more familiar conditions. The difference in energy between these states is substantial, enough to drive significant heating when the phase transition finally occurs. As Atlas gradually warms during its approach to our Sun, even by just a few degrees above its interstellar equilibrium temperature, the amorphous ice begins to undergo crystallization. The phase transition releases latent heat as water molecules reorganize themselves from their disordered amorphous arrangement into the more stable hexagonal crystal structure of normal ice. This crystallization heat provides an internal energy source that can drive water sublimation independently of external solar heating. But the process becomes self-sustaining through a feedback mechanism that amplifies the initial crystallization events. As crystallization releases heat and drives sublimation, the loss of water vapor creates voids and fractures within the comet's interior. These structural changes allow heat to penetrate deeper into the nucleus, triggering additional crystallization in previously unaffected regions. The result is a cascading process where crystallization begets heating. Heating drives sublimation, and sublimation creates conditions for additional crystallization in a self-reinforcing cycle that can continue for months or years. Computer models of this process reveal remarkable complexity in the thermal evolution of amorphous ice-rich objects. The crystallization doesn't occur uniformly throughout the nucleus, but propagates inward from surface regions as heat waves that move through the interior at speeds determined by the thermal conductivity of the ice and the energy release rate of the phase transition. Different regions of the nucleus may crystallize at different times, creating complex spatial patterns of energy release that could explain the observed temporal variations in Atlas's water emission. Even more intriguingly, the crystallization process may be enhanced by the presence of trace compounds mixed with the water ice. Laboratory experiments have shown that small amounts of methanol, carbon monoxide, or other volatiles can catalyze the amorphous to crystalline phase transition, lowering the activation energy required for the process to begin and increasing the rate at which it propagates through the ice matrix. If Atlas contains such catalytic compounds, distributed throughout its interior as a result of the chemical environment in which it formed, the crystallization process could be far more efficient than pure water ice models predict. The comet could be experiencing a form of internal combustion, where the energy release from crystallization is amplified by chemical reactions involving trace species that were incorporated during its original formation around an alien star. But crystallization may represent only one component of the internal energy budget. Atlas has been exposed to cosmic ray bombardment throughout its millions-year journey through interstellar space, and these high-energy particles have gradually altered the chemical structure of materials throughout its interior. Cosmic rays break molecular bonds, create free radicals, and drive chemical reactions that produce compounds not normally found in equilibrium ice. The energy deposited by cosmic ray impacts accumulates over geological timescales, stored in the form of chemical bonds that are thermodynamically unstable, but kinetically trapped at the low temperatures of interstellar space. As the comet warms, even slightly, these stored chemical changes can begin to reverse, releasing the energy that was deposited by cosmic ray bombardment over millions of years of exposure. The result is what some researchers have called a cosmic ray battery, an energy storage system that accumulates charge over millions of years and then discharges that stored energy when triggered by modest temperature increases. If Atlas contains such energy storage systems distributed throughout its interior, they could provide a sustained heat source that operates independently of crystallization processes. Perhaps most remarkably, the internal heating of Atlas may be creating conditions where liquid water can exist temporarily within its frozen interior. If crystallization and cosmic ray energy release can raise local temperatures above the melting point of ice even briefly, they create environments where complex aqueous chemistry becomes possible within the comet itself. These transient liquid regions would represent mobile chemical laboratories, where reactions could occur that have no equivalent in the static chemistry of purely frozen systems. Complex organic synthesis, mineral dissolution and precipitation, and even primitive metabolic processes could potentially occur within the warm, liquid-rich environments created by internal heating processes. What if the fire we see streaming from Atlas isn't sunlight at all, but memory? The accumulated thermal history of a million-year journey, stored in molecular bonds and crystal defects and chemical disequilibria, finally finding expression as the comet encounters the gentle warmth of our distant sun. The comet burns not with borrowed energy from our star, but with the banked fires of its own long passage through the galactic night. In this view, Atlas becomes more than a passive chunk of ice responding to external heating. It becomes an active system, powered by energy sources that span the history of its existence, capable of complex internal evolution and chemical development that continues throughout its journey between the stars. The fire inside burns with the accumulated energy of cosmic evolution itself, transforming the comet from a simple frozen relic into a dynamic participant in the ongoing chemistry of interstellar space. As Atlas continues its slow journey toward the outer reaches of our solar system, its brilliant tail gradually dimming as distance from the sun increases and the internal fires that drive its water emissions slowly subside. We find ourselves contemplating not just the fate of this particular visitor, but the broader questions of impermanence and legacy that its passage raises about the nature of existence in a universe that tends toward dispersal and decay. The comet that blazed so dramatically in ultraviolet light just months ago will eventually fade below the detection limits of our most sensitive instruments, becoming once again a silent wanderer in the cosmic dark. Its magnificent tail of water vapor and dust will dissipate into the interplanetary medium, scattered by solar wind and radiation pressure, until no trace remains of the spectacular display that captured the attention of astronomers around the world. Yet the dispersal is not complete destruction, but rather transformation, a change of state that distributes the organized chemistry of Atlas throughout a much larger volume of space. Every water molecule that escaped the comet as gravitational grasp carries within its atomic structure the isotopic signature of an alien star system. Every dust grain shed from its nucleus preserves the chemical fingerprints of processes that occurred under conditions unlike anything found in our own solar neighborhood. This dispersed material will not vanish, but will become part of the background inventory of interplanetary space, available for incorporation into the formation of new objects or the evolution of existing ones. Some will be captured by the atmospheres of planets, adding alien chemistry to the ongoing evolution of these worlds. Some will be swept up by the solar wind and carried to the outer reaches of the solar system, where it may eventually become incorporated into the formation of new comets in the Oort cloud. The process mirrors the life cycles of all organized systems in the universe, from the largest structures down to the smallest. Galaxies form from the gravitational collapse of primordial gas clouds, evolve through billions of years of stellar birth and death, and eventually disperse as the expansion of space carries their constituent stars beyond the reach of mutual gravitational attraction. Stars ignite from the collapse of molecular clouds, burn through their nuclear fuel over millions or billions of years, and then scatter their processed elements back into space through stellar winds and explosive death throes. Planets aggregate from the dust and debris of stellar systems, evolve through geological processes that create and destroy surface features over millions of years, and eventually lose their atmospheres to space, or are destroyed by the death of their parent stars. Even life itself follows this pattern, emerging from the chemical complexity of planetary environments, evolving through countless generations of reproduction and selection, and ultimately dispersing its accumulated genetic information through extinction and speciation events that redistribute biological diversity across space and time. At every scale, the universe appears to operate according to principles that favor the temporary concentration of matter and energy into organized structures, followed by the eventual dispersal of that organization back into more distributed forms. The second law of thermodynamics describes this tendency in terms of increasing entropy, the inexorable progression from ordered states to disordered ones, from concentrated forms to dispersed ones, from organized complexity to randomized simplicity. Yet the story of Atlas suggests something more nuanced than simple decay from order to disorder. The comet's passage through our solar system represents not just the destruction of an organized object, but the redistribution of organized information throughout a larger system. The chemical signatures embedded in its ice and dust carry data about formation processes, isotopic ratios, and chemical environments that existed around another star billions of years ago. This information doesn't disappear when the comet disperses, but becomes distributed throughout the interplanetary medium, where it can influence the future evolution of our solar system. The alien chemistry carried by Atlas becomes part of the chemical heritage of our local space environment, potentially affecting the composition of objects that form or evolve in the future. In this light, the dispersal of interstellar objects like Atlas represents not entropy in the simple sense of increasing disorder, but a more complex process of information distribution and sharing. The organized chemistry of one star system becomes input for the chemical evolution of another, creating connections and continuities that span the galaxy. The perspective transforms our understanding of cosmic evolution from a simple progression toward increasing disorder to a more complex process of information cycling and redistribution. The universe may tend toward dispersal, but that dispersal doesn't represent pure destruction. It represents the sharing of organized information across ever larger scales of space and time. Every comet that disperses its nucleus across interplanetary space contributes its chemical information to the ongoing evolution of its host system. Every star that scatters its processed elements through stellar winds or explosive death provides raw materials for the formation of new generations of stars and planets. Every galaxy that disperses through cosmic expansion carries with it the accumulated chemical heritage of billions of years of stellar evolution. The echoes in the dust are not just the fading traces of objects that once existed, but the ongoing influence of their organized chemistry on the evolution of the larger systems they have joined. Atlas will eventually fade from view, but its chemical signature will persist in the interplanetary medium of our solar system for millions of years, potentially influencing processes and events that we cannot yet imagine. Perhaps most poetically, the dispersal process ensures that no organized system ever truly disappears, but rather becomes distributed throughout the larger context in which it existed. The information content of the system, its chemical signatures, isotopic ratios, and structural organization, becomes part of the background from which future systems will emerge. In watching Atlas fade into the cosmic background, we observe not the death of a wanderer from another star, but its transformation into a permanent part of our solar system's chemical heritage. The comet dies as a discrete object, but lives on as a distributed influence that will affect the evolution of our local space environment for eons to come. Every mystery in the sky eventually becomes part of the dust from which new mysteries are born. Every visitor becomes a permanent resident, not as a discrete object, but as a distributed memory, woven into the chemical fabric of the cosmos itself. In those quiet moments when we step outside and crane our necks toward the star-filled darkness above, searching among the familiar constellations for some sign of the cosmic visitor that has captivated our scientific instruments and our imagination, we participate in a ritual that connects us across time to every human being who has ever wondered about their place in the vast arena of existence. The water streaming from Atlas cannot be seen with unaided eyes. Its signature exists in portions of the electromagnetic spectrum that human vision cannot access, revealed only through the sophisticated instruments that extend our senses far beyond their biological limitations. Yet the comet's presence in our solar system speaks to something fundamental about the human condition and our relationship with the cosmos that surrounds us. We are a species driven by curiosity about origins. Where did we come from? How did the materials that compose our bodies, our world, our entire solar system, first come into existence? What processes operating across cosmic time and galactic distances led to the emergence of a planet where complex chemistry could evolve into biology, and biology could evolve into consciousness capable of contemplating its own existence? These questions reach beyond simple scientific inquiry to touch the deepest philosophical and spiritual concerns that have motivated human thought throughout recorded history. Every culture that has ever existed has developed creation stories that attempt to explain how the familiar world of daily experience emerged from the vast unknown that lies beyond immediate perception. Atlas offers a different kind of creation story, not the mythology of gods and supernatural forces, but the equally profound narrative of chemistry and physics operating across scales of space and time that humble human imagination. The water in the comet's tail carries within its molecular structure the direct record of processes that occurred around an alien star under conditions that existed billions of years ago in places we will never visit. Yet that same water, those same basic chemical building blocks, compose the majority of our own bodies. The hydrogen and oxygen atoms that make up the H2O molecules streaming from Atlas are fundamentally identical to the hydrogen and oxygen atoms that flow through our bloodstreams, fill our cells, and enable the biochemical processes that sustain our lives. This realization transforms our relationship with the comet from that of distant observers studying an alien object to something more intimate and personal. We are not separate from Atlas, isolated on our small world while it passes through our cosmic neighborhood. We are made of the same stuff, governed by the same physical laws, participants in the same vast chemical network that connects every object in the galaxy through shared atomic heritage. The perspective shift is both humbling and elevating. Humbling because it reveals the cosmic scales on which the processes that created us operate. We are not the central focus of creation, but incidental participants in chemical evolution that spans billions of years and countless star systems. Elevating, because it reveals our deep connection to the larger cosmos. We are not aliens in a hostile universe, but native participants in cosmic processes that operate throughout the galaxy. When we look up at the night sky and contemplate the invisible presence of Atlas somewhere among the stars, we are looking at family. Not biological family in any sense that evolution on Earth would recognize, but chemical family. Objects composed of the same fundamental building blocks, shaped by the same physical forces, participating in the same cosmic processes that have operated throughout the galaxy's history. The realization extends beyond Atlas to encompass our relationship with the entire cosmos. Every star we see overhead has undergone nuclear fusion processes that created the heavy elements necessary for planet formation and biological chemistry. Every galaxy visible through our telescopes contains billions of star systems where these same elements are being recycled through planetary formation, geological evolution, and potentially biological development. We exist within a vast web of chemical relationships that spans the observable universe. The calcium in our bones was forged in the nuclear furnaces of massive stars that died billions of years ago. The iron in our blood was created during supernova explosions that scattered heavy elements throughout the galaxy. The carbon in our DNA underwent complex chemical evolution in molecular clouds, on planetary surfaces, and perhaps within the interiors of comets like Atlas during their long journeys between stars. This chemical genealogy reveals that every mystery we observe in the sky is really a reflection of processes that occurred during our own formation and evolution. When we study Atlas, we are studying our own cosmic heritage. When we analyze the isotopic ratios in its water vapor, we are reading chapters from the same chemical history that led to the formation of our own world. Perhaps every mystery in the sky is really a reflection of what we seek within ourselves, an understanding of our place in the cosmic order, our connection to processes that operate on scales far larger than individual human experience, our participation in chemical and physical evolution that extends back to the origin of the universe itself. The questions that Atlas raises about the formation and evolution of planetary systems are ultimately questions about our own origin and development. How common are water-rich environments, like the one that gave birth to life on Earth? How frequently do interstellar objects carry the chemical building blocks of biology between star systems? What processes operating throughout the galaxy have contributed to the specific chemical conditions that made our existence possible? These questions cannot be answered by studying our solar system alone, because our local environment provides only a single example of how planetary formation and chemical evolution can unfold. Atlas and other interstellar visitors provide crucial additional data points, samples from different chemical environments that reveal the range of conditions and processes that exist throughout the galaxy. In seeking to understand these cosmic visitors, we are really seeking to understand ourselves, not as isolated biological entities living on a single world, but as expressions of cosmic chemistry that has been billions of years in development, as participants in galactic processes that connect us to every other organized system in the observable universe. When we look up at the night sky, we are looking into a mirror that reflects our own chemical heritage back at us, written in the light of distant stars and carried by messengers like Atlas across the patient darkness of interstellar space. Throughout this long meditation on water and wandering, on chemistry and cosmic connection, we have followed Atlas through its passage across our solar system with the assumption that its most remarkable feature, the massive emission of water vapor from an object so far from the sun, represents the central mystery that demands explanation. But now, as our cosmic visitor fades toward the outer darkness, and we reflect on all that we have learned from its brief sojourn in our neighborhood, a deeper realization emerges. The water isn't the strange part. Water is, as we have discovered, one of the most common compounds in the universe. It forms readily wherever hydrogen and oxygen encounter each other under the right conditions of temperature and pressure. It exists in vast quantities in molecular clouds, where it condenses onto dust grains in the frigid depths of interstellar space. It fills the atmospheres of giant planets and the subsurface oceans of icy moons throughout our own solar system. It streams from the nucleus of every comet that approaches our sun, sublimating from solid to gas as solar radiation heats their frozen surfaces. Even the extraordinary scale of Atlas's water emissions, remarkable though they may be, can be explained through the physics of amorphous ice crystallization, cosmic ray energy storage, and internal heating processes that operate according to well-understood principles of chemistry and thermodynamics. The comet's behavior pushes the boundaries of what we have observed before, but it doesn't violate the fundamental laws that govern matter and energy throughout the universe. The strange part is the realization that these visitors are not rare. For decades, astronomers theorized about the existence of interstellar objects, while acknowledging that detecting them would require extraordinary advances in observational technology, combined with remarkable good fortune. The spaces between stars are vast beyond human comprehension, and any objects wandering through those spaces would be invisible until they approached close enough to our sun to reflect sufficient light for detection by our most sensitive instruments. The conventional wisdom held that such objects would be exceedingly rare visitors to our solar system, perhaps one detected every few decades if we were lucky, and only then if it followed a trajectory that brought it close enough to Earth for observation before disappearing back into the cosmic dark. Yet within the span of 8 years, we have detected 3 such objects. 3 separate messengers from alien star systems, each carrying its own chemical signature, each displaying behavior that expands our understanding of the diversity of materials and processes that exist throughout the galaxy. The statistical implications are staggering. If we have detected 3 interstellar objects within such a brief observational window, the total population of such wanderers must be enormous. Conservative estimates based on detection rates and observational biases suggest that the space around our solar system may contain millions of interstellar objects at any given time, most too small or too distant to detect with current technology. But the implications extend far beyond simple population statistics. If interstellar objects are common rather than rare, they transform from curiosities worthy of individual study into representatives of vast populations that connect every star system to every other through ongoing exchange of materials and chemistry. The galaxy emerges not as a collection of isolated stellar systems, each developing according to its own local conditions, but as an integrated network of chemical communication where the building blocks of worlds flow freely between stellar neighborhoods. Every star system both contributes to and receives from this galactic recycling program, ejecting some of its small bodies into interstellar space while capturing wanderers from other systems. The process operates on timescales that span the entire history of the galaxy. For billions of years, objects like Atlas have been wandering between stars, carrying chemical information from dying planetary systems to regions where new worlds are forming. The materials that compose our own solar system may include significant contributions from interstellar objects captured during the early phases of planetary formation, making every world in our system a hybrid creation that incorporates materials from throughout the galactic neighborhood. This perspective revolutionizes our understanding of planetary formation and evolution. Instead of viewing each star system as an isolated chemical laboratory, we must consider the possibility that planets throughout the galaxy share a common chemical heritage, connected by the wandering traffic of interstellar objects that carry materials and information between stellar systems over cosmic time. The implications for the search for life are profound. If the chemical building blocks of biology are regularly transported between star systems by interstellar objects, then the development of life becomes not just a local phenomenon that must arise independently in each planetary system, but a galactic process that can spread the precursors of biology throughout entire stellar neighborhoods. Regions of the galaxy that have experienced high rates of stellar formation and planetary system evolution may be enriched in organic-rich interstellar objects, creating favorable conditions for life to emerge in subsequently forming systems. The chemical complexity necessary for biological development may be shared between worlds through the medium of wandering comets and asteroids, creating connections and continuities that span the galaxy. But perhaps the most profound implication of Atlas' visit is what it reveals about the nature of the universe itself. We have grown accustomed to thinking of space as empty, punctuated by occasional islands of matter organized into stars and planets, separated by vast gulfs of nothingness. The reality suggested by interstellar objects is very different. Space is not empty, but filled with wandering chemistry. The voids between stars teem with objects carrying the accumulated chemical heritage of billions of years of stellar evolution and planetary formation. These wanderers create threads of connection that link every star system to every other, weaving the galaxy into a unified whole where chemistry and information flow freely across distances that seem to represent absolute barriers to communication and exchange. The universe is not silent, but constantly whispering through the medium of wandering objects that carry between worlds the molecular signatures of their birth environments. Every interstellar visitor represents a message encoded in chemistry and physics, a communication from one part of the galaxy to another, written in the universal language of atomic structure and molecular bonds. Atlas has taught us that we are not isolated on our small world, cut off from the broader galactic community by the immense distances between stars. We are part of a vast network of chemical communication that has been operating throughout the galaxy's history, connected to every other star system through the patient wandering of objects that carry between worlds the very substances from which planets and life are made. The strange part is not that water streams from a comet born around another star. The strange part is the realization that such streaming represents just the visible manifestation of a much larger process. The constant circulation of matter and chemistry throughout the galaxy, carried by countless messengers that connect every world to every other world through bonds of shared atomic heritage. We are not alone in the cosmos, not because of the presence of other conscious beings, but because we are part of a galactic community of chemistry that includes every star, every planet, every object that has ever existed or will exist throughout the history of the universe. The boundaries we imagine between one star system and another, between our local chemistry and alien chemistry, between familiar and foreign, dissolve in the face of the deep connections that bind all matter into a single, unified whole. The universe is not empty. It's whispering, and we are finally learning to listen. In the outer reaches of our solar system, beyond the orbit of Neptune where sunlight dims to little more than starlight and temperatures approach the absolute zero of interstellar space, something new moves against the background of distant stars. The discovery came not through the planned observations of major observatories, but through the patient scanning of automated sky surveys that continuously monitor the heavens for objects that don't belong in our catalogs of known asteroids and comets. The object appears as little more than a moving point of light, barely distinguishable from the background stars except for its subtle motion relative to the celestial sphere. Its trajectory, when calculated from multiple observations spanning several weeks, reveals the telltale signature of hyperbolic motion, the mathematical fingerprint of an object not bound by our sun's gravity, another wanderer from the depths of interstellar space. Initial designations place it as 4I, the fourth confirmed interstellar object detected within our solar system. Its discoverers, following the tradition established by Oumuamua, Borisov, and Atlas, will eventually bestow upon it a name that reflects its origin in the space between stars. But for now, it remains simply another catalog number, another entry in the growing database of cosmic visitors that have revolutionized our understanding of the galaxy we inhabit. Preliminary observations suggest that this new visitor carries its own secrets, its own chemical signature, that will add another chapter to the story of interstellar diversity. Spectroscopic analysis hints at composition different from any of its predecessors, perhaps rich in organic compounds or containing exotic ices that formed under conditions unlike anything seen before. The object appears larger than Atlas, possibly more active, with early indications of a developing coma and tail that suggest vigorous outgassing as it approaches the inner solar system. But the discovery of a fourth interstellar object within a decade represents more than just another scientific opportunity. It confirms what Atlas began to suggest, that such visitors are not rare anomalies but regular participants in the ongoing evolution of our solar system. The space around our sun appears to be filled with wandering chemistry, a constant traffic of materials and information flowing between stellar systems throughout the galaxy. Observatories around the world are already turning their instruments toward this new arrival, eager to decode whatever messages it carries in its chemical composition and physical behavior. The lessons learned from studying Oumuamua, Borisov, and Atlas have taught us what to look for. Isotopic ratios that reveal formation conditions, outgassing patterns that speak of internal structure trajectories that carry information about the gravitational environment of their birth systems. Each new visitor adds another piece to the puzzle of galactic chemical evolution, another data point in our growing understanding of the diversity of environments that exist around other stars. The pattern that emerges from these multiple observations suggests a galaxy far richer in chemical diversity than our local experience might indicate. A cosmos where planetary formation occurs under an enormous range of conditions, producing objects with compositions and behaviors that continuously surprise and educate us. The steady stream of interstellar visitors also transforms our perception of humanity's place in the cosmic order. We are not isolated observers studying a distant and alien universe from our small perch in space. We are participants in an ongoing galactic conversation conducted in the language of chemistry and physics, recipients of messages that have traveled across light years and millions of years to share with us the accumulated wisdom of cosmic evolution. As the fourth interstellar object approaches the inner solar system, it carries with it the promise of new discoveries, new insights into the chemical diversity that exists throughout the galaxy, and new connections between our local environment and the broader cosmos that surrounds us. Its water, if it contains water, will add its voice to the chemical symphony that Atlas has already contributed to our solar system's ongoing evolution. Its dust will become part of the interplanetary medium that connects all objects in our cosmic neighborhood. But perhaps most importantly, its arrival confirms that the age of interstellar visitors has only just begun. What we have witnessed with Oumuamua, Borisov, and Atlas represents not a series of rare and isolated events, but the opening chapters of a new era in astronomy, where such objects become routine rather than extraordinary. The next decade may bring dozens of interstellar visitors, each carrying its own chemical heritage from distant star systems, each adding new layers to our understanding of the galactic community to which we belong. Our solar system will be enriched by chemistry from throughout the local stellar neighborhood, transformed from an isolated island of familiar materials into a crossroads where the accumulated chemical heritage of multiple star systems mingles and evolves. In the patient darkness beyond Neptune's orbit, something approaches, not an alien in the sense of conscious intelligence from another world, but something equally profound, chemistry from another star system, materials that formed under alien conditions, carrying within their atomic structure the direct record of processes that occurred in places we will never visit, under the light of stars whose names we do not know. The universe continues to whisper its secrets through the medium of wandering objects that cross the boundaries between star systems, carrying messages encoded in molecular bonds and crystal structures that tell the story of cosmic evolution across scales of space and time that humble human imagination. Something else is coming, and with it, new chapters in the ongoing story of our connection to the cosmos that surrounds us, new evidence that we are not alone in the galaxy, but part of a vast community of chemistry that includes every star, every planet, every object that participates in the grand dance of matter and energy that has been unfolding since the universe began. The whispers from space grow stronger with each passing year, carried by messengers that bridge the vast distances between worlds, connecting us to the broader galactic community through bonds of shared atomic heritage that reach back to the origin of the elements themselves. We are listening, and the universe has much more to say. If you found yourself drawn into this cosmic journey of discovery and connection, consider exploring more stories that bridge the gap between rigorous science and the profound wonder of our place in the universe. The cosmos is vast, but through careful observation and thoughtful contemplation, we find that we are not separate from it. We are part of its ongoing story of chemical evolution and cosmic connection.